Welcome to Manasi's Math Solution. Today we are going to discuss about normal groups, normal subgroups and factor groups. So this is our second module of abstract algebra. So let's start. We know that for an abelian group G, if G is an abelian group, then for any A, B in G, AB is equal to BA. Suppose H is a subgroup of G. Suppose H is a subgroup of G. And let A be any element in G. Now consider AH. What it means by AH, which is a coset. What is this? This is equal to the set of all elements in the form A product B, where B belongs to H, or in other words we write it as, which is the set of all AH, not generally we denote AH such that H belongs to H. So this is the set AH, and here G is an abelian group and H is a subgroup of G. Now consider HA. HA is the set of all elements in the form H product A, where H belongs to what? H. And is these two sets are equal? Is these two sets are equal? Yes, because when we consider an element in this AH, any element in AH is in the form AH for some H in H. And since G is abelian, we have AB equal to BA for all elements in G. And here A and H are elements in G, therefore we can write it as AH is equal to HA. And this is true for all H in H. So this implies that AH is equal to HA. So for an abelian group, when we consider any subgroup H of G, we have this property: AH is equal to HA for any A in G. Okay. Now consider a non-abelian group. In that group, for any subgroup H of G, AH need not be equal to HA. And what happens if there exists a subgroup H of G with the condition AH is equal to, which satisfies the condition AH is equal to HA for all A in G. Here G is a non-abelian group, and for a non-abelian group, these two sets need not be equal. Okay. And if there exists any subgroup H of G which satisfies this condition for all A in G, we call it as normal subgroup of G. Normal subgroup of G. So what is a normal subgroup of a group G? What is a normal subgroup of a G? When we say that a subgroup H of G is normal, we say that a subgroup H of G is normal if and only if AH is equal to HA for all A in G. This must be satisfied for all A in G, not for some A. This must be satisfied for all A in G. Okay. So this is a normal subgroup. So So from our first explanation we can say that if G is an abelian group, then every subgroup of G will be normal in G. Okay, every subgroup of an abelian group is normal. So for next example, consider S3. S3 means set of all permutations of 3 elements. So identity element 1 2 1 3 2 3 1 2 3 1 3 2. These are the elements in S3. Each of these are functions from 1 2 3 to 1 2 3. Each of these are 1 1 functions from 1 2 3 to 1 2 3. The bijective functions, one bijective function. Each of these are bijective functions from the set 1 2 3 to 1 2 3. And what it means by this is this cycle 1 2, which means 1 maps to 2, 2 maps to 1 and 3 maps to 3. And 1 3 is that 1 maps to 3, 2 maps to 2 and 3 maps to 1. And what it might mean by this cycle, 1 maps to 1, here 2 to 3, 2 to 3, so 2 to 3 and 3 to 2, 3 to 2. Next 1 2 3, look at this cycle, 1 maps to 2, so 1 to 2, 2 maps to 3, so 2 to 3, 3 maps to the first element 1, and the last one is that 1 2 3, 1 maps to 3, 3 maps to 2 and 2 maps to 1. Okay, so these are the elements. Now consider this subgroup H is equal to E, which means identity set 1 2 3, sorry, the permutation 1 2 3, permutation 1 2 3 and 1 3 2. Now this is actually what, A3. Now we need to check that is this subgroup A3 of S3 is normal. This subgroup A3 of S3 will be normal if A3 is equal to A3A for all A in S3. So generally we denote the elements in S3 by sigma, so I am writing it as sigma, small letter sigma. Now let sigma is equal to 1 2. Then let us find the coset 1 2 A3. What will be this set? So first we need to operate 1 2 with the identity, and this is 1 2 itself, and next operate 1 2 with the element 1 2 3, and the operation will be in this order. Here 1 maps to 2, and look at the first element in this second permutation. That is, the second permutation is the cycle 1 2 3, and look at the first element 1, and 1 maps to 2. Now look at the first cycle, first element. Here 2 maps to 1, so 1 maps to 2, 2 maps to 1, so 1 to 1. Next consider the second element 2. Here 2 maps to 3. And now look at the first cycle. Here 3 maps to 3. So 2 maps to 3. Now look at the second cycle. Here 3 maps to 1, and in the first cycle 1 maps to 2. So here it is 2, and this is equal to what? Here this is the cycle 2 to 3, 3 to 2. So 2, 3. Now find 1, 2, 1, 3, 2. 1, 2, 1, 3, 2. And this is equal to, here 1 maps to 3, and in first cycle 3 maps to 3. So 1 to 3. Next 2. Here 2 maps to 1, and in the first cycle 1 maps to 2. So here it is 2. And in the second cycle 3 maps to 2, and in the first cycle 2 maps to 1. So here it is 1, and this is equal to the cycle 1, 3, 3, 1. So 1, 3. Okay. Hence the set 1 to A3. The coset 1 to A3 is equal to the set 1, 2, 2, 3 and 1, 3. Now let us find the coset, right coset A3, 1, 2. Note that AH is the left coset and HA is the right coset. Okay, so let us find the right coset of A3, and this is equal to the set identity 1, 2 and 1, 2, 3, 1, 2 and 1, 3, 2, 1, 2. We know that E identity into 1, 2 is equal to 1, 2 itself, and 1, 2, 3, 1, 2 is equal to 1, 2, 3, 1, 2 is equal to 1, 2, 3. Here 1 maps to 2, and in the first cycle 2 maps to 3. So here 3. Here 2 maps to 1, and in the first cycle 1 maps to 2. So here it is 2. And in this cycle 3 maps to 3. And so in the first cycle 3 maps to 1. So this is 1. And this is equal to the cycle 1, 3. And 1, 3, 2, 1, 2 is equal to, in the same way we can say that this is equal to what? 2, 3. So the coset, right coset will be is equal to 1, 2, 1, 3, 2, 3. Now look at this cosets. Here A3, 1, 2, 1, 2, A3 and A3, 1, 2 are same. So 1, 2, the both of these cosets are equal. In this same way, we can prove that for any sigma in S3, sigma A3 is equal to A3 sigma. So A3 is a normal subgroup of S3. And here S3 is a non-abelian group. S3 is a non-abelian group, and here A3 is a normal subgroup of S3. Consider a subgroup H of G which satisfies the condition AH is equal to HA for some A in G. And note that AH is equal to HA does not means that AH is equal to HA for all H in H. This does not means that AH is equal to HA for all H in G. For example, consider this normal subgroup A3 of S3 and consider the products 1, 2, 1, 3, 2 and 1, 3, 2, 1, 2. We know that 1, 2, 1, 3, 2 is equal to 1, 3 and 1, 3, 2, 1, 2 is equal to 2, 3. These two cycles are not equal. Here these two products are not equal, but we have the cosets A1, 2, A3 is equal to A3, 1, 2. So what is a normal subgroup? A subgroup H of G is called as normal subgroup of G if and only if AH is equal to HA for all A in G, and we denote it by this notation, which means H is a normal subgroup of G. H is a normal subgroup of G. Okay. Now, next we are going to prove a result, theorem 9.1, and this is actually a normal subgroup test. This is actually the normal subgroup test, and this result gives an equivalent condition for a group to be a normal subgroup, and the statement is that a subgroup H of G is normal if and only if what? X inverse is contained in H, is contained in H for all X in G. So if for some subgroup H of G, for any X in G, X inverse contained in H implies that H is a normal subgroup of G, and if H is a normal subgroup of G, then that subgroup H satisfies this condition for all X in G. So here we need to prove this result. For the proof, let's start with the part H is a normal subgroup of G. So here we need to prove that XH X inverse is contained in H for all X in G. Since H is a normal subgroup of G, for any X in G, we have XH is equal to HX. For any X in G, we have XH is equal to HX, and we need to prove this inclusion. For that, let H belongs to H and consider the element XH X inverse in the set XH X inverse. So here consider this element and okay, we have when we consider this X and this H, okay, when we consider X and this H, we have XH belongs to the coset XH, and since H is normal, XH is equal to HX. So this implies that XH belongs to HX, and this implies that XH is in the form H dash X for some H dash in H. And now operate with x inverse from the right side, then we will get x inverse is equal to h dash, and h dash is an element in h. So this implies that x inverse belongs to h. So any element x inverse in the set x inverse is in h. Therefore the set x inverse is contained in h. So we have proved that if h is a normal subgroup of G, then for any x in G, x inverse is contained in h. Next we need to prove that if for any x in G, if x inverse is contained in h, then h is normal. So let us assume that for any x in G, x inverse is contained in h. Now let x is equal to a, then this implies that a inverse is contained in h. Then this implies that ah is equal to ha. Sorry, ah is contained in ha. How we can say that ah inverse is contained in h implies that ah is contained in ha. So let us prove that. Consider an element ah in ah. Okay, so ah is in ah. Then for this ah, consider A inverse, which is an element in A inverse, right? This is an element in A inverse because all elements in A inverse is in this form for some h in h, and hence AH, and not that, and we have AH A inverse is contained in H by our assumption. So this implies that AH A inverse is belongs to H. So AH A inverse is equal to H dash for some H dash in H. Okay, now operate this equation by A from the right side, then we will get AH is equal to H dash A. Then this implies that here H dash A is in what? HA. Okay, H dash A is in HA, and H dash A is equal to what? AH. So this implies that AH belongs to HA, which means any element AH in this left coset AH belongs to the right coset HA. So AH is contained in HA, and here we need to prove HA is contained in AH. If we proved it, then we can say that these two cosets are equal. For that, to prove this, let x is equal to A inverse. X is equal to A inverse. Then from this we will get A inverse H. A inverse, all inverse is contained in H, and this implies that A inverse H A is contained in H. And here we have proved that AH A inverse is contained in H implies that AH is contained in HA. In the same way, we can prove that A inverse HA contained in H implies that HA is contained in AH. So from these two inclusion, we can conclude that the cosets AH, the left coset AH is equal to HA. So we can say that for any A in G, AH is equal to HA, hence H is a normal subgroup of G. So from this result, we can say that a subgroup H of G is normal, which means H is a normal subgroup of G if and only if X inverse is contained in H. Okay, now we are going to discuss some extra examples. Let G be a group and consider the trivial subgroup of G, that is the subgroup which consists of identity only. And for any A in G, what is, suppose this is equal to H, and what is AH A inverse, which consists of all elements of the form AH A inverse such that H belongs to H. And here there is only one element in H, and which is identity. So this is equal to A E A inverse. And what is A E A inverse? Here E means identity. So A E A inverse equal to A inverse, and this is equal to identity. So this is equal to H. And for any A in G, AH A inverse is equal to H. Therefore, by the result, theorem 9.1, we can say that H is a normal subgroup of G. So for any group G, its trivial subgroup is a normal subgroup. Now consider the improper subgroup, the whole group itself, which is also always a subgroup of G for any group G. And for any A in G, AG A inverse is equal to G itself. So we can say that G is a normal subgroup of G. So for any group G, its trivial subgroup and improper subgroups are what? Normal subgroups. Now consider the center of a group. It is defined for any group. For any group, we can define the center of a group. And what is the center of a group? The center of a group is the set of all elements G in G such that AG is equal to, or GA is equal to AG for all A in G. That is, if for some G in G, if GA is equal to AG for all A in G, which means G commutes with every element in this group. If G commutes with every element in a group, then G will be in the center of that group. Okay, So we can directly say that center of a group consists of all elements which commutes with every element in a group. Okay, now we are going to prove that for any group G, the center of that group will be a normal subgroup of that group. So we need to prove this. For that consider an element A in G, and A center of G is equal to, what is this left coset, which consists of all elements A, G such that G belongs to the center of G. This is the actual set, and which is equal to, here center of G consists of all elements which satisfies this condition. So for this AG is equal to GA. So here we can write GA such that G belongs to the center of G. And what is this set? This is the right coset of center of G. This is equal to center of G, A. So for any A in G, we have A center of G is equal to center of G, A. Right? So we can say that the center of a group is always a normal subgroup. For any group, this is true. For any group G, the center of that group is always normal. These three examples are main examples for a normal subgroup, and this will exist. These normal subgroups exist for all groups, for any kind of groups. Next we are going to prove that the alternating group. What is the alternating group? Which is AN, which contains all even permutations in Sn. So alternating group is a normal subgroup of Sn. For any n greater than or equal to 3, AN is a normal subgroup of Sn. And what is AN? AN consists of all even permutations in Sn. When we say that a permutation is even, we say that a permutation sigma in Sn is even if it can be written as even number of transpositions in Sn. If it can be written as the product of, even number of transpositions. Next we are going to prove a result, and the result states that let H be a normal subgroup of G and K be a subgroup of G. Here H is a normal subgroup and K is a subgroup. Then HK, what it mean by HK? HK consists of all elements in the form H product K, where H in H and K in K. This will be a subgroup of G. So the result states that when we consider a normal subgroup and a subgroup of G, this set will be a subgroup of G. So let us prove this result by using subgroup test. And the subgroup test states that for any a subset H of G is a subgroup of G if and only if identity belongs to H, and for any AB in H, AB inverse belongs to H. So H will be a subgroup of G if it satisfies this condition. Now we are going to prove that here HK is a normal subgroup of G. For that, here H is a normal subgroup of G and K is a subgroup of G. So identity belongs to both of these sets, H and K. Therefore, by taking E product E, we will get the identity E, and this belongs to HK. Now let H1 K1 and H2 K2 belongs to the set HK, where H1 H2 belongs to H and K1 K2 belongs to what? K. And consider H1 K1 H2 K2 inverse, and this is equal to H1 K1 K2 inverse H2 inverse, and this is equal to H1 K1 K2 inverse H2 inverse. Now K1 K2 inverse is an element in G, and H2 inverse belongs to what? H. Therefore, K1 K2 inverse H2 inverse is an element in the left coset K1 K2 inverse H, right? And hence, and here H is a normal subgroup. Therefore, this left coset is equal to H K1 K2 inverse, right? And hence we can say that this element is in this right coset. Okay, so there exists a H dash in H such that K1 K2 inverse H2 inverse is equal to what? H dash K1 K2 inverse. Now we can write this as H1, this is equal to H1 H dash K1 K2 inverse. Here H1 and H dash are belongs to H, therefore this product belongs to H, and K1 K2 are elements in K, therefore K1 into K2 inverse belongs to K. So these two are elements in H and K, therefore these two elements are not both in H and K. The first part is in H and the second part is in K, and therefore the product will be in HK, which means H1 K1 H2 K2 all inverse is in HK for all H1 K1 in HK, H1 K1 and H2 K2 in HK. Therefore, by subgroup test we can say that HK is a subgroup of G. Next question is that suppose H is a subgroup of G and K is a subgroup of G, then is this implies that HK is a subgroup of G. This is not true for all H and K. If H is normal, then this is true. If H is normal and K is a subgroup of G, then HK is a subgroup of G. That we have proved it. In general, this is not applicable because, for example, consider G is equal to S3 and let H is equal to identity and the element 1, 2 and the cycle 1, 2. This is a subgroup of S3. Now let K is equal to identity and 1, 3. Now consider HK. HK consists of all elements identity 1, 3 and 1 2 identity and 1 2 1 3, and this is equal to identity into identity is identity, identity into 1 3 is 1 3, and 1 2 into identity is 1 2, and 1 2 into 1 3. What is 1 2 into 1 3? Here 1 maps to 1 2 3, 1 maps to 3, and in first cycle 3 maps to 3. Here 2 maps to, in this cycle 2 maps to 2, and in first cycle 2 maps to 1, and in this cycle 3 maps to 1, and in first cycle 1 maps to 2. So this is 2. So 1 3 2 1, 1 3 3 2 2 1. So this is equal to 1 3 2. So HK consists of the elements identity 1 3 1 2 1 3 2. Here HK is not a subgroup of S3. Why? Actually there are 6 elements in S3, which means the order of S3 is equal to what? 6. And from this the order of HK is equal to 4. But 4 does not divide 6, which means S3 does not have any subgroup of order 4. Therefore HK is not a subgroup. In other way, consider the product what? 1 2 1 3. 1 2 1 3 is equal to 1 2 3. Here 1 maps to 3, and in first cycle 3 maps to 3. Here 2 maps to 2, and in first cycle 2 maps to 1. Sorry, already we have seen 1 2 product 1 3, which is in HK. Sorry. Consider 1 3 product 1 2. This is equal to 1 2 3. Here 1 maps to 2, and in first cycle 2 maps to 2. Here 2 maps to 1, and in first cycle 1 maps to 3. Here in this cycle 3 maps to 3, and in first cycle 3 maps to 1. So what? And this is equal to 1 2 2 3 3 1. So 1 2 3, and 1 2 3 is not equal to 1 3 2. So therefore this is 1 3 1 2 1, and okay, and 1 3 1 2, which is not equal to 1 3, which is not equal to 1 2, which is not equal to 1 3 2. Therefore this is another element, and if HK is a group, is a subgroup, then the product of any two elements must be in HK. And here 1 3 product 1 2 is equal to what? 1 2 3 1 2 3, and this is does not belongs to HK. Therefore HK is not a subgroup. From this example, we can say that the result is not applicable for two arbitrary subgroups. That is, H and K subgroups of G does not means that HK, the product HK is a subgroup of G. If H is a normal subgroup of G and K is a subgroup of G, then this implies that HK is a subgroup of G. Okay, now we are going to prove another result, and the statement is that if a group G has a unique subgroup, unique subgroup H of some finite order, then H is normal in G. The result states that if a group G has a unique subgroup, if G has a subgroup H of, if G has a unique subgroup H of some finite order. If G has a unique subgroup of some finite order, then H is normal in G. To prove this, we know that H is a normal subgroup of G if and only if GH G inverse is contained in H for all G in G. Okay. Now consider the set GH G inverse. This is actually a subgroup of G. How it will be a subgroup of G? Let us prove this. For that, consider the identity element in H. Then G E G inverse is equal to G G inverse, and this is equal to identity. So identity belongs to what? GH G inverse. Now consider two elements in GH G inverse. Let it be GH1 G inverse and GH2 G inverse. Let these two elements are in GH G inverse, and consider the product GH1 G inverse GH2 G inverse, and this is equal to all inverse, and this is equal to GH1 G inverse product G inverse all inverse means G, H2 inverse G inverse, and this is equal to GH1 G inverse G by grouping these two terms, H2 inverse G inverse, and which is equal to GH1 H2 inverse G inverse. We know that H is a subgroup. Therefore, for any two elements H1 H2 in H, H1 H2 inverse, the product H1 H2 inverse is also in H. So this is an element in H. Therefore, G H1 H2 inverse G inverse is in GH G inverse. That is, for any two elements A, B in GH G inverse, the product AB inverse is also in GH G inverse. This means that the set GH G inverse is a subgroup of G. So GH G inverse is a subgroup of G. For any subgroup H, and for any element G in G, GH G inverse is a subgroup of G. And what is the order of the subgroup GH G inverse? The order of this subgroup is equal to order of H, because GH G inverse consists of all elements in the form GH G inverse for each H in H. For each H in H, GH G inverse is in this group, subgroup. Therefore, order of GH G inverse is equal to order of H. Now we have proved that for any subgroup H of G and for any element G in G, GH G inverse is a subgroup of G with the order GH G inverse. The order of GH G inverse is equal to order of H. Now suppose H is a subgroup of G. H is a subgroup of G. H is a unique subgroup of G with the order n. suppose H is a unique subgroup of G with the order n. We have proved that for any G in G, GH G inverse is a subgroup of G, and the order of GH G inverse is equal to the order of H, and the order of H is equal to n. So this implies that GH G inverse is a subgroup of G of order n. But by our assumption, H is the unique, H is a, not A, H is the unique subgroup of G with the order n. So for this GH G inverse must be equal to H. So for any G in G, GH G inverse is equal to H if H is the unique subgroup of G with the order n. And hence this implies that what? H is a normal subgroup of G. Okay, so if H is the unique subgroup of G with the order n, then H will be a normal subgroup of that group. Okay.